So about theory of light-matter interaction, and then more specifically into X-ray matter interaction. So I brought a few, let's say, examples. Don't worry if you can't read all the pictures. It's just to give you somehow an idea what we can use theoretical X-ray spectroscopy for. So it could be either for structural fingerprints. This is a very well-known application of X-ray spectroscopy. It could be for probing methodology, but also for simply characterizing and exploring a class of materials. Overall, I think putting results from theory and experiment together will give us insight into the interactions in a material. So you have seen this before, of course. So where are we aiming at? We're aiming at a frequency range or a wavelength range of something like 10 to the power of minus 10 meters. So an angstrom, which is comparable to the lattice spacing. But as you will see from the, let's say, explanations of the theory, we don't care too much about which kind of light we are looking at. So for us, the methodology is pretty the same, whether we're looking into the optical range or the X-ray range. So in that sense, we have a free electron laser, a theoretical one, because we can tune our frequencies according to our needs. So then we start very slowly, very basics into light-matter interaction. And I need to say also, of course, I will show you that the quantum mechanical treatment of matter is very important. If you're not interested in the matter of light itself, we can treat light basically on the classical level. So we basically can start from Maxwell's equations, from Maxwell's theory. So, and there I start with the response functions. So what is this for? What we want to know is how a material reacts to an external perturbation. So light comes with an electric field, this disturbs the system, and we would like to see how the system responds to this. So in that sense, we can, for instance, expand the polarizability of the material in terms of the component of the electric field that comes from the light. And so we have, if in the spirit of the Taylor expansion, we have linear and higher order coefficients. But if we stick for the moment to the linear order, then we can relate let's say, the electric field components to various other properties we're interested in. So for instance, the susceptibility, the response function high, relates the polarizability with the electric field, or the conductivity relates the current with the electric field. Most important, this is the quantity that we're going to compute, is the dielectric tensor, which relates the displacement to the electric field. So what is the dielectric tensor about? It's quite a pretty complicated object, as you see here. It relates R and R primes as a non-local quantity. That means if I disturb my system somewhere at a certain space, I can probe later on at a given time, for instance, T prime or T, how the system reacts at a different place in the sample. So it's pretty complicated. So say it's non-local in time. It depends also on in the time difference, and non-local in space. But it's not typically the quantity that we compute. We like more to go to the Fourier transform of it, and doing so, we give up the space coordinates in view of in the favor of G and G prime, so the Fourier coefficients, and instead of the time, we go to frequency space. So first of all, what does this G and G prime mean? So I've told you before, R and R prime means that we can disturb the system at some space, but then we probe what is the reaction on the other space. G and G prime is similar. Like if you think about that, you can expand the density and the potential in terms of a Fourier series. That would mean you disturb, so to say, one component of the potential, the G component, and you would see a reaction on the G prime component in the density. Most important here, and this gets me back to the frequency dependence, the dielectric function depends on the frequency, and that way we can probe, as I said, optical, infrared, whatever frequency range we are interested in. So as long as we can compute the dielectric tensor, dielectric function, we have access to all kinds of frequency ranges. So this is the object of desire, epsilon gg prime as a function of omega, but there's also a q, and this q is the momentum transfer. Well, one more thing, this is on the microscopic scale. This is how we compute it microscopically, but what is finally measured is the macroscopic dielectric function, so m, which is the inverse of the inverted tensor, and here we take the 0, 0 component. But still, we have the omega dependence here, we have the q dependence here, and the q, as I said, this is the momentum transfer. So this is the first place where we have to distinguish between visible light and X-rays, because momentum transfer for visible light is considered to be negligible. So if you think about a wave coming in with an optical wavelength, so it spans, so to say, the wavelengths spans many of the lattice spacing. Lattice spacing is in the order of an angstrom, but the frequency or the wavelength is 4 orders of magnitude larger. So in that sense, if you take the inverse of lambda, which gives you the momentum, which can be considered basically 0. However, if you go to X-rays, which have a comparable wavelength to the lattice spacing, this is nice because that's why we can use it for probing the structure with diffraction. The momentum transfer is not negligible anymore because it's the same order of magnitude, and we have to take into account also this fact. So, what about other optical constants? As the dielectric function, or the imaginary part of the dielectric function, is typically the object that we compute, but we may be interested in all the other optical constants. Of course, nothing of this is constant because everything here depends on the frequency. But anyway, having the imaginary part of epsilon, we can get to the real part by Kramers-Kronig transform, for instance, or we can also compute it directly. We can get access to the optical conductivity, which is basically imaginary part of epsilon multiplied with the frequency. We can compute the complex refractive index, reflectivity, absorption coefficient, loss function, you name it, whatever we are interested in. Once having computed one of these response functions, we have access to everything else. So finally, we also should think about symmetry. Probably look at this index here. What I've shown before, the epsilon is not only dependent on frequency and Q, it also depends on the light that comes in, the direction of light or the polarization of light comes in, and the polarization of light that we are probing, the outgoing light, and this makes the dielectric constant not only a function of omega, but it also makes it a rank 2 tensor in terms of this polarization direction. So in a triclinic system, where we have basically no symmetry. The only symmetry is that the tensor itself is symmetric, so we have 6 different components. For monoclinic lattices, we still have 4 different components, also rhombic 3, tetragonal, hexagonal 2, and finally, the cubic material is completely isotropic. It doesn't matter where, in which direction I shine in light or probe the light, we always get the same answer. So, I'm mainly going to talk about absorption experiments. So let's have a look at how a theorist considers what happens in an experiment. So you have a material, you have your occupied bands. So as said, it doesn't matter whether these are valence states or core states. You have your unoccupied bands here. And when you shine in light, you will take an electron from the occupied region to the unoccupied one. So it occupies then a different electronic level, and this process can be described, as said, by the dielectric function, and this expression that I point out here is basically Fermi's golden rule. So what does this mean? The light that is coming in has to have a frequency which fits into the distance between 2 different bands. So this is basically energy conversion. And this which tells us that the imaginary part of epsilon will have the peaks exactly at the distances between 2 bands. Okay? But nothing tells us so far whether this transition is allowed or not. So it could well be that this is a dark, well, this is dark, it's not allowed. And the selection rules are given by these quantities here. So these are the momentum matrix elements between the occupied and the unoccupied points, and this is where the direction of light, or the polarization of light, comes in, alpha and beta. And this tells us, so if we have very large matrix elements, then we have a strong oscillator strength, we would have very high peaks. If we don't, if these symmetry rules, the selection rules are not fulfilled, we wouldn't see much in the spectrum. Also, we have to integrate over the whole Brion zone, because this excitation can happen anywhere in K-space. And of course, we have to sum also about all the conduction and valence bands, or core states and conduction states, because transitions can happen also between different bands. So far, so good. This is a very, let's say, simple expression. Still, of course, we don't know how we compute it, where our knowledge is coming from. Actually, we call this the independent particle approximation. And independent, why independent? Because this electron that is excited from the occupied states and goes to some empty state doesn't care about its history, so to say. It doesn't care about the hole that it has left behind. So this space down here is completely independent of the excited electron. This brings me to my outlook, so to say. What I'm going to discuss here is how can we compute this. So we have seen so far a simple formula. The question is, how do we get all the ingredients to compute it? Then we may ask the question whether this expression also applies to the core states. And finally, we'd ask the question whether this picture is good enough. Obviously not. So this independent particle approach, in particular for core states, is not so well suited. But I will show you, give you kind of a little crash course into electronic structure theory in order to tell you how we can compute it and how we can do it better. So let me introduce you to state-of-the-art methodology for treating many-body systems. So matter is a very complicated thing. We have many particles in a sample, we have many electrons, all of them interact with each other. And the question is how to treat them. Of course, we need to go to the ground state first in order to know how we can excite this ground state. So how do we do this? Well, I don't ask you here, but the answer you will definitely give me. We can describe it simply by solving many-body Schrodinger equation, isn't it? So this is a very beautiful equation. It applies to everything that we're interested in matter. The question is how we can solve it. Well, in fact, we can't solve it because it's much too, or not solve it directly, because it's much too complicated to solve. So we have to find a way out. And the reason is because this many-body wave function depends on all the coordinates of all particles. And even if you consider a many-body wave function of just a few electrons, we wouldn't be able to solve it. So the Schrodinger equation is considered in mathematics to be an MP-hard problem, simply not solvable. So what's the way out? Obviously, we can do quite a bit on computational material science nowadays. So we have to go to an alternative description of our many-body system. And this brings me to our favorite ground state theory, which is density functional theory. Now, this is my first question to you, because I would like to know what your somehow background is. Can you tell me, so who of you never heard about density functional theory? Who has basic knowledge? Who has enough knowledge in order to somehow understand some literature, reading some literature? And who is an expert in this field? You go from red, blue, green, and yellow. Okay, this is great. We have many people with a lot of knowledge. We have also some people who have never heard about it. So, do we have experts here? Okay, thank you. So I try to do my best somehow to accommodate your knowledge. Actually, just feel free to ask me also in between, because I don't want to lose any one of you. So, what is density functional theory about? So, what you see here, in essence, it puts the electron density as a key variable, and this is very nice because Hornberg and Kohn have shown in 1964 that you don't need the explicit knowledge of the many-body wave function. It's good enough to know the electron distribution. And this is a huge step you can consider. So now you don't need an object. It depends on all coordinates of all the electrons you have, but you also only need an object which depends on 3 coordinates, x, y, and z. This is the density depends on x, y, and z. And they have shown, actually, it has been used before. Density has been used before, also in the late 20s, already in the late 20s of the 20th century. But Hornberg and Kohn somehow set the stage in proving that this is in fact so, such that you can express the total energy as a functional just of the electron density. And so you can compute the total energy just knowing the density, and you can also compute all the materials properties in the same way as a functional of the density. So this is great, and now I would like to show you why we love this theory so much, because it allows us to treat atoms, molecules, clusters, quark systems, surfaces, interfaces, even nanostructures on the same footing. So it's the same theory, it's one equation that we have to solve, and this one equation can solve the problems of all these materials in general. So, I'll show the equation in a second, but this is actually the reason. It's a very universal theory, and this is the reason why density functional theory is nowadays the workhorse of material science. So how does this equation look like? This is the so-called Kohn-Sham equation, which we use for the ground state. It looks like this. So basically, it has a kinetic energy term, it has an effective potential, and it comes with single particle energies and single particle wave functions, Kohn-Sham energies and Kohn-Sham wave functions. So what you see here is, in fact, a single particle Schrodinger equation. So we have got away from this complicated many-body Schrodinger equation. We just need to solve a single particle-like equation. The essence is that one electron that we look at, so it only depends on the electron coordinate, it depends, or it feels the interaction with all the other electrons just by this effective potential. So the Hartree potential, the classical interaction, and the quantum mechanical bit of electron-electron interaction. So I told you before, so you can compute atoms, bulk systems, whatever you like. So they only distinguish between the external potential, because this is the potential which comes from the nuclei, so the Coulomb attraction between the nuclei and the electrons. But the equation itself, the form, the program that you use is the same for all the materials that you're looking in. So the question is, how come that I can replace this many-body Schrodinger equation by single-body Schrodinger equation? Now this is a trick. I've put it up here already, because we replace this many-body system of interacting electrons, which would require the many-body wave function, by a fictitious system of non-interacting electrons. So if you start from electrons, each of these electrons interacts with the other by Coulomb interaction, you go to a system of electrons which seemingly don't interact because they feel the interaction with all the other electrons by this effective potential. Now, having this said, I have to warn you at the same time, because having this done, because this is a fictitious system, this has been introduced, and the beauty of this is that both of them have exactly the same density. That means we can use this fictitious system to get the exact ground state density, and with this we can compute the exact properties, so to say, given that this bit here is good enough, because this is the only bit exchange correlation potentially where we have to make approximations for. So the theory is exact with one approximation that we do here. So now comes the warning, because now these single particle energies basically don't have any meaning, because they have been introduced as Lagrange parameters of the minimization principle, so we cannot interpret them. The wave function themselves also don't have a meaning, so they become very close to the exact ones, I have to say. But the meaning of them is still that they produce the exact density here. But what we call here the Kohn-Sham band structure shouldn't be interpreted a priori. I come back to this. So This is nice. We have found the single particle-like equation to be solved for our many-body problem, but the problem is these energies here, the band structure cannot be interpreted. So that means if we want to go to excited states, we have to do better. And doing better means that we go up in methodology. But now I have another question for you. So which of the answers is correct? Walter Kohn was awarded the Nobel Prize for Physics in 1999. Kohn-Sham theory was developed in 1963. Walter Kohn was awarded the Nobel Prize for Chemistry in 1998. Or the Hornberg-Kohn theorem is exact for ground state and excited states. What do you think? Okay. Many of them, most of them are very good. There are a few of them which are not correct. So let me tell you, Walter Kohn was awarded the Nobel Prize because his work was really considered essential for computational materials chemistry. Actually, he was not awarded the Nobel Prize for Physics, and it was not in 1999. Kohn-Sham theory was not developed before the proof of the Hornberg-Kohn principle, so this was in 1965. This is the right answer, and unfortunately, the Hornberg-Kohn theorem and Kohn-Sham theory doesn't work for excitations, and this is the bad bit because now I have to take you to the next step of theory. So, how do we do in order to describe the band structure? Let me again show you how a theorist thinks about an experiment. In this case, I'd like to introduce the photoemission experiment to you. So again, we have all our band structure with field states. Here we have conduction bands. We again shine light onto a sample, but now the light is much more energetic, such that it kicks out an electron. This is what you would probe in photoemission. And from the electron that is kicked out, from the kinetic energy, you can get some information about the valence band states or lower lying states. Likewise, if you bring in an electron, light goes out. This is the inverse photoemission process, which will give us information about the conduction bands. If you combine both of them, for instance, we get access to the electronic band gap. So how do we describe this? Obviously, we have to describe not an n-particle system, but a system with a particle going away or coming in. So we have to go to Green's function theory. How does this work? What do we need? I mean, we have somehow boiled down the many-body system of interacting electrons to a fictitious system of non-interacting electrons. And since this system was fictitious, we were not allowed to interpret the energies. What we want to have, however, is also in principle, single particle energies that we are allowed to interpret. Because single particle energies are dear to us. We don't want to somehow think about the whole system at the same place. We want to consider one state as a final state or excited state or as an initial state of an excitation. So we would like to have single particle energies, states, that consider these many-body interactions. These are not fictitious systems. And this brings me to the quasi-particle concept. This is the idea of Richard Mattock. I very much can recommend his book on many-body systems. This is, I think it pictures the whole thing very nicely. So if you ride a horse through the desert, you have this very nice and clean horse, but after a while you will see that this horse is getting dressed with all the interactions on the way, so it's collecting all kinds of dirt in this kind of picture. And you consider the formation of a quasi-particle in the very same sense. You start from a real particle, but then this real particle feels the interactions with all the surroundings. Could be electron-electron interaction, but you also could treat the same thing, electron-phonon interaction, electron-magnon interaction, whatever you think of. So all the interactions an electron is exposed to can be cast into a new kind of particle that we call a quasi-particle. And this quasi-particle is between the interaction between the quasi-particle now is very small and negligible, such that we can interpret these quasi-particles with its energetic states. So how can we picture that. So we start from our bare electrons. We shoot in light. After a certain time step, we will see in a photoemission experiment, for instance, that an electron has been ejected, and a missing electron can be considered like a positive charge that it has left behind. And then you will see after a certain time that the system is polarized because, of course, this positive charge somehow will be attractive for the neighboring electrons. So it will, this hole that is created will be dynamically screened. And if you look the system up after another time step, you will see that this hole has moved, but now it has been surrounded by electrons because of this attractive force between electron and the holes. Dynamical screening is important here, but as I said, you can imagine that this is basically the formation of a quasi-particle which consists of this hole, but with this electron cloud around it. So screening is very important, and that's why the key quantities in green function theory to describe this is, first of all, the dielectric function, and as a second step, the dynamically screened Coulomb interaction. So the Coulomb interaction is not the bare Coulomb interaction between all these particles, because think about an electron that is sitting here will feel the Coulomb interaction very, very, let's say, bluntly from a neighboring electron. But if this electron is sitting far away, there are many other particles in between which screens this interaction, and that's why it's much more appropriate to consider, instead of this bare Coulomb interaction, so this 1 over r potential here, the dynamically screened one. This is the essence of Green's function theory. So, and this allows us now to go up the next step. As I said, the Conchem eigenvalues, they are not allowed to be interpreted, but still they are not so bad. I mean, they still somehow, in an effective way, include the interaction with these others through this exchange correlation potential. But we have to do better in order to have interpretable energies. And for this, we have to somehow correct these Conchem eigenvalues by in a simple approximation by first order correction in perturbation theory. Now, in this Conchem equation, the quantum mechanical beta, the electron-electron interaction, is considered by this exchange correlation potential. In a real world, so to say, in the quasi-particle equation, this electron-electron interaction is treated by the self-energy. The self-energy is a non-local quantity, so the potential here is local. The self-energy is a non-local quantity, and you can compute it from this Green's function. And that way, to make this the long story short, you can update your Conchem system by correction terms in order to get the so-called quasi-particle energies that we now can interpret in terms of excitation energies. Now we are ready for excitations, but of course the theory that we have seen here just gives you the energetic states of single particles and still doesn't tell you how a system is excited if you shine in light. So we have to do better even, which means that we have to go up again in the methodology ladder and see how we can compute spectra. So I go back to my picture that we have seen already. So we shine in light, we excite an electron, but now, and this I have indicated here, we also want to consider that this electron that has been excited sees the hole that it has left behind. So electron is negatively charged, the hole is positively charged, so obviously it may have some attractive force between the electron and the hole, thereby forming so-called electron-hole pairs, which are also called excitons, and are again another type of excitations which we can consider as a quasi-particle. It's not fermionic, we have two electrons together, but it's another type of quasi-particle. And this is what we like to describe, these electron-hole pairs and the interaction between these two charges. So, question to you. In which systems do you consider these excitonic effects, this Coulomb interaction between electron and the hole, to be most strongly bound? Could this be the optical absorption of insulators? Could this be the low loss spectra of metals? Could it be deep core excitations in semiconductors? Or could it be scenes of molecular crystals? What do you think? Okay, we have pretty mixed opinions. I don't see any. Well, I see one answer. I see one correct answer. So, thank you. But in fact, besides the metals, where I will argue in a minute, it's least important. All the other answers, there's also something to it, and I don't tell you the solution now, because I'm going first of all to examples at the end, but also to the equations, which somehow would tell you what the answer could be. So in essence, we go up in theory, and what we compute now is this so-called Bethe-Salpeter equation, which includes, besides the interactions of the many electron system or many hole system, which we can treat by these levels of methodology below, we now include also a term that takes into account the electron-hole interaction, so the Coulomb interaction between these two charged particles. The solutions of this are here. It's again a Schrodinger-like equation. The solutions of this are the energies of these two particle states and the coupling coefficients between these core and conduction states. I'll show you some examples for this in a second. Let me just go very roughly to some equations. I don't show many of them. You don't need to be afraid of too many, but I have to walk you through a few of them still. So how does this effective electron-hole Hamiltonian look like? In fact, it has three different components. The first one is pretty simple. We call it the diagonal term because it only consists on the energetic distance between the initial state and the final state, so core state and conduction state. So if you would throw away the Coulomb interaction between the electron and the hole, this would give you the independent particle approach. So that would mean that the frequency of light just has to fit between these two states. That's a simple one, but life is not so simple. We have to include now the Coulomb interaction between electron and the hole, and this comes with a direct term, which is attractive, of course, because you have an electron and the hole, positive and negatively charged particles, and we have an exchange term which is repulsive. So compared to the independent particle approach, this term would shift your peaks to the red, and this term would shift your peaks to the blue. Actually, this term here takes care of local field effects, of the local variation of your potential. I'll show an example to this later in the second half. You can see both of these terms are very cumbersome to compute. It scales basically like Hartree-Fock. You have this product of these four wave functions. Very important so here is that again, this attractive Coulomb interaction is screened by the dielectric function. So it's the same concept like before. Before we have seen that the electron-electron interaction is screened by the dielectric tensor or matrix. Here, the electron-hole interaction is screened. And this gets me back to the questions I've been asking you. So think about in which of these materials the screening is most or least effective. In metals, we have very high electron densities, and that's why the dielectric function is pretty high. So metals will be perfectly screened, and in metals you can more or less safely forget about the electron-hole interaction. It's more or less because if the metal is good, you can do so. If you have bad metals, there could be also excitonic states, maybe not at the absorption onset, but at higher energies or in core states. Semiconductors, we have smaller electron densities, so the screening is less efficient than in metals. And here we have exciton binding energies in the valence range of the order of a few milli-electron volts. If you go to the core, these are higher. Insulators, again, very localized states. Screening is very bad, so we have very strong excitonic effects. Molecules are basically the worst case because there is no screening, in particular in small molecules, and in addition, the electron and the hole basically are sitting at the same space. So they're both sitting on the molecule, so they feel this attractive force between the electron and the hole very, very brutally. So in this makes a second distinction here between optical spectroscopy and core spectroscopy, because if you go down to the core, the initial states, the core states, are also very localized, and localized states mean that we have stronger Coulomb interaction between the electron and the hole. So typically, core excitations have stronger or larger binding energies than valence excitations. So let's go to the core. I have to admit something first, because I have walked you through all the theory going from DFT to GW to Bethe-Salpeter equation. I have to admit here that for most of the Bethe-Salpeter equations, not for all of them, but for many, we sometimes ignore or leave out the GW step. And the reason is the following. Even if in GW you get relatively reliable excitation energies, even if you have a very small error, a small relative error, if you go to the core energies are so large that the small relative error gives you a big absolute error. In that sense, it's very hard to reach the absolute onset of a core transition, and that's why we have to shift the spectrum anyway to the experimental spectrum, and then you can leave out this cumbersome step. But sometimes we need to correct at least the conduction bands. So after having admitted this, I'd like to go back to the Bethe-Salpeter equation. You have seen already, we have this eigenenergies here, we have the coupling coefficients, we have the Hamiltonian. Now I've written it down in terms of core states and unoccupied states, not valence conduction, but core and unoccupied. I just want to tell you how you would see electron-hole interaction in the spectrum. So first of all, what we have seen before in the independent particle approach is that the selection rules or the oscillator strength is only governed by these momentum matrix elements. Okay? Now, the transition coefficients, and if you square them, this is the oscillator strength, they're renormalized by the coupling strength. So if the coupling strength is 0, then these coefficients would be 0 and 1, so you would be back to the independent particle picture, so oscillator strength would be okay. If the coupling is strong, then you would strongly renormalize your oscillator strength. So compared to the independent particle picture, if you switch on the Coulomb interaction, you may see some arrangement of oscillator strengths. More important probably is that if you look at the expression for the dielectric function, there you see here the peaks which were produced by the distance before between an occupied and unoccupied band. They would be shifted because now the peak position are at the two-particle excitation energies. So again, if the coupling is very small, then these excitation energies are the distances or very similar to the distances between two bands. If the coupling is strong, you would see some peak shifts. And I'll explain this to you later on when I show you some examples, just to make sure how we would see the effect of electron-hole Coulomb interaction in a spectrum. So with this methodology in hand now, we can explore various core edges. So we can go up, for instance, from the deep-lying 1s state. So this would be a K edge exciting in 1s electron. Or if you go to the second shell, the n=2 shell, we have the L edges, L1, the S states, L2, L3 for the two P states, which are spin-orbit split. Or you can go up to the next shell, n=3. This would be the M edges. So the methodology can be applied to any of them, and I'm going to show you a few examples of this. So before this, now we have basically half the time. Probably instead of making a break, I would be happy to answer questions which just are related to the methodology, if you like. No, actually, we start from Green's function series. As I say, we solve the two-body. I mean, if you use Green's function series, so for the single particle equation, we have to solve the Dyson equation. So we start from the non-interacting picture from the Conchem Green's function and propagate it such that we get the solutions of the interacting Green's function. And for the two-body Hamiltonian, we have to employ two-particle Green's function and the according equation. So for the one-particle Green's function is the Dyson equation. For the two-particle Green's function, it's the Bethe-Salpeter equation. So it has the diagrams, the two diagrams which are inside is the attractive Coulomb term and the repulsive. So it's another approach. I'm not starting from wave functions. I'm starting from Green's function. Okay, so then, yeah, sure.
You showed this hierarchy of equations, or the equations for the Bethe-Salpeter equation, and you showed these different terms. So how do they depend on the choice of the exchange correlation function?
Yeah, I think this is a good point. Of course, probably I may go back. Yeah, I go back to this one. So, I mean. What I show here is the first order approximation to the Conchem system. In principle, this GW approach is a self-consistent thing. So you can start from anything. You even can start from the pure Hartree picture. This was how the Haydn's equation were derived from. The closer you are to the truth with your exchange correlation functional, the better this first order perturbation theory is. So if not, then you either don't end up with the perfect answer, or you have to choose another functional to start with in order to make this term here small, or you need to do a self-consistent GW in order to catch up for the error that you have done in this here. We also have explored starting point dependence in the Bethe-Salpeter equation. And from what we find is, of course, you carry it up to this step. What we find is that this step from the Conchem states to the Green's function, to the self-energy to GW, is more crucial. So the energies, energy difference is here. So if you have some failure here from the functional, this impacts also the spectra most. But it's an important point. This is the only approximation we have to use. And that's why, of course, all the results that we're producing still may suffer from the approximation that we're doing below.
But the question that she asked, I think, was more for the light matter interaction, whether you use the dipole approximation.
Probably. So sorry, I didn't get. I thought you were talking about multipolar expansion, which are typically done in a. No, we're using the dipole approximation here. Yeah. So linear order and dipole approximation. Okay. Thanks for clarifying. So let me go to examples, and I start with a material coming from the solar energy research. These are castorites. Castorites have been a very promising family of materials for solar absorbers before the advent of perovskites. So I think now everyone is going into perovskites, and we also have done some calculations for this. Still, I would like to use this example somehow to show you what kind of analysis we can do with the methodology that we have in hand. So, castorites, interesting because they are non-toxic and they have cheap and abundant ingredients. So it's copper, zinc, tin, and sulfur, and probably remember the color code because I will use it also in the next transparencies. Okay. So what you see here on the right-hand side is the L23 edge. Actually, this is dying, maybe another one. So the L23 edge, that means we excite p states from the core, and that means that the final states for such excitations, according to the selection rules, must be S-like or D-like. And for this reason, I'd like to show you in a minute, or in half a minute, the band structure and the composition of the conduction states. Thank you. That's great. Okay, so this is the spectrum, imaginary part of the dielectric function. What you see here is the comparison between the Bethe-Salpeter equation and the independent particle approximation. I think this is one of the beauty of theory, that we can switch on and switch off our interactions according to our needs. Experiment cannot do this, but the comparison of this gives us some idea how important this electron-hole interaction is. Sorry. And obviously, it's pretty important because, as I said before, what you observe here is a shift of the peaks. So obviously, we have strongly bound excitons here. You also see this line here, the gray line, is the absorption onset you would expect from the independent particle approach. So we have a peak below. That means we have an exciton with a binding energy of a few tenths of an electron volt. But you also see that there is quite some redistribution of oscillator strengths because of this interaction of the electron and the hole. So, as I said, we're exciting electrons from the p states. That means that our final states are S and V-like character. So let's have a look how our band structure looks like. So don't worry, this is the same picture on both sides. It just is the band structure of this material. But what we have highlighted here with the color code, on the left-hand side, all the states which have D-like contribution. And on the right-hand side, all the states which have S-like contribution. And you see there's a lot of S and D character around here. That means we would have large oscillator strengths. I would expect large oscillator strengths all over the energy range here. Particular point to this picture here, which is a hybridization between tin and sulfur, also with some admixture of copper D states here. So now we can also analyze the L2 and the L3 splitting. So in principle, we do the calculation for both L2 and 3 together because there's spin-orbit split with an energy of 1.22 electron volts. So we have an interaction between L2 and L3. Also, we can identify regions in this excitation spectrum where the character, mostly the low energy excitations or excitons, mainly have L3 character. And also here we have L3 character. In the middle we have L2-3 character. So there's hardly any excitons with L2 character alone. So this is bound states here below the gap, and you see that this peak here is not formed only by one exciton, but we have several contributions to this. Now I have to tell you what these symbols here mean. So these symbols are the solutions of the Bethe-Salpeter equation. So these are the energies here. These are the energies of these excitations coming out from this two-body equation. And the height of these symbols indicates the oscillator strength of these individual excitations. And then if you sum up all these excitations, we end up with this spectrum. I've picked out one excitation here with L3 character. This is the one with the highest oscillator strength. And this I would like to discuss with you in more detail. So first of all, we can identify, of course we know the initial state, but we can identify from our analysis where the final states are. And the final states are obviously coming here from a very small, no, not so small, but a region around the gamma point of the lowest conduction band. So this is known from our analysis. So let me say something to this extension here, because the electron hole binding energy is very strongly related to the extension of this electron hole pair. So if you have a very large binding energy, that means you have a strong Coulomb interaction, and this would mean that the electron and the hole obviously are very closely or sitting very close to each other, such that this Coulomb interaction is strong. So that means that the electron hole wave function has a limited extension, so it's pretty localized if the binding energy is large. On the other hand, if you go to K-space, you would expect the opposite. If the electron hole pair is localized in space, it's delocalized in K-space. So for a large binding energy, you would expect contributions from all over the place in the Brion zone. Opposite, if you have a small binding energy, that means electron and the hole are far away from each other. That means the electron hole pair is pretty much delocalized in real space. And then, in this case, it could happen that the contribution to an exciton in terms of final state comes from a very, very tiny region of the Brion zone. This is the case, for instance, in SP semiconductors, where we have binding energies of milli-electron volts, where we can very often see that the only contributions to this exciton comes from basically the gamma point with a tiny, tiny region around. Okay? Here we see some intermediate picture. That means the contributions in K-space are not too small, not too localized, but also not very widespread. So it's an intermediate binding, which we see, you can read also from the binding energy that we see here. Now let's have a look at the exciton wave function. As said, the exciton wave function is a two-body object, so it depends on the coordinate of the hole and the coordinate of the electron. It's a six-dimensional object in general, so it's very hard to plot. But for core states, we're lucky because we know exactly where the hole is, namely in the atom that we have excited. So in this case, we know exactly that the hole is sitting in the sulfur atom here, and we can basically explore what the electron distribution around this hole is. And this is what you see here. Again, it's an intermediate binding situation where the electron hole pair is not too much delocalized, so it's staying within one unit cell, but at least it spreads out to a few neighbors of this atom that we have excited. Just one more word to the way we compute this exciton wave function. So remember, we have to solve a two-body equation. That means we need to come up with some basis functions for these two-body functions. And what we do is we expand these electron hole pairs in terms of all possible products of initial states and final states that we have from our ground state calculation. So we know from the ground state all core states, all unoccupied states, all the wave functions, and we build all possible products of them, and then we let the Hamiltonian, by minimizing the Hamiltonian, choose which of these products are most favorable and will form an electron hole pair. And in this respect, we can also analyze very nicely which of the contributions we have to a given excitation, what are the binding strengths, these coefficients in between here. So, last but not least, you are interested in how this compares to experiment. I would say not perfect, but also not too bad, because this material is pretty complicated. We have two experiments here, one from the Helmholtz Center in Berlin, and the other one from National University of Singapore. As you can see, the theory, the result beta equation, agrees quite nicely with experiments in this low energy range, also in this onset here. We have some more discrepancies in the higher energy region, but we also have to see that experiments do not fully agree with each other. And the reason is simply because this is a pretty complex material. There's lots of defects in it, and anti-side pairs and whatnot. And I don't show it here, but doing calculations for defected crystals, we see that we can pretty much resolve this puzzle here between theory and experiment. So overall, I would say the agreement is pretty satisfactory here. Let us go to something completely different now. These are organic molecules. So we abandon the crystalline world and we go to molecules. What you see here is isobenzene SAMs, self-assembled monolayers on a gold surface. So this is the molecule. It consists of two benzene rings, which have a nitrogen bridge in between here. And the excitations we are going to look at is the K edge of nitrogen. So we excite the 1s states of these nitrogen atoms here. So let me give you first a little bit of a motivation why we are interested in these materials. Isobenzenes are switches. So these are molecules that change their conformation, the structural conformation, upon shining light on them. So if you shine in light, they will change the geometry. If you shine in another light frequency, they will switch back to the original geometry. So one of these frequencies in the visible range, the other of the frequencies is in the UV range, I think. But why are we interested in it? So of course, such switches could be very useful for devices, for switches. However, I mean, a floating molecule in the device is not very useful. And that's why in order to use it for an application, you have to put such a molecule on the surface. But then people found if you put them on the surface, they don't switch anymore. So they're not useful anymore for switching. And there are actually two reasons for this effect, why they're not switching anymore. One is the interaction with the surface itself. That's very interesting because, for instance, if you put it on a metal surface, because this could be at the same time your electrode, then you would change the frequency of switching, if it switches at all. This is a different thing. But at least it changes the frequency, and for two different reasons. And you know the reason already, because this is the dielectric screening. So this metal surface somehow adds additional screening, because it's a very polarizable medium. And this additional screening would change Bose. It would change the electronic band gap of this molecule. So it would lower the band gap. But at the same time, it would also lower the exciton binding energy, because it also adds additional screening to the electron-hole interaction. So overall, the excitation energies would change quite drastically. Well, people have found a way around, and you see this already. So if you don't put the molecules directly on the surface, you can prevent the interaction between these two by linkers, which basically lift them up such that they are further away from the surface. So actually, it's also not the topic I'm talking about. We've done some calculations here. But I would like to address the second reason why they don't switch anymore. Because, as you see, they form very nice self-assembled monolayers. So very nicely crystalline packed structures. And this may be the reason why they, another reason why they don't switch anymore, because they start to talk to each other when they are excited. So if they're close to each other, due to this packing, they don't have the same excitation properties anymore like the bare molecule. And this is what I would like to show you. So first of all, I show you some experiment. This is Nexaf's experiment from Martin Weinel's group at the Free University in Berlin. In essence, I show you again already the theory here. What we see in Bose, we have at the lowest excitation, we have a very strong pi star excitation, which goes from the core to the LUMA, lowest unoccupied molecular orbital. And at higher energies, here we have further pi star excitation, which go to higher lying molecular levels. And this is also what we see here. Now, at the first glance, you also see in comparison the independent particle picture. So what would happen if you switch off the Coulomb interaction? You say it's a disaster because the spectra look completely different. At least they are shifted. They don't look completely different. They still have some strong peaks, but they're very much shifted due to electron-hole interaction. But we have excellent agreement with experiment in Bose, in this peak structure here, and also in the character, going to LUMO and to LUMO plus higher energies. So what about packing? What you see here down, we have computed excitations of 3 different situations. One is the isolated molecules. One is the packed structure, like it appears in the experiment, where we have 2 molecules per unit cell. And in addition, just to see the intermediate range, we also have computed what we call a diluted SEM, where we only have 1 molecule in the unit cell. So this is pretty complicated. What you see here is again the comparison of Bethe-Salpeter equation with the independent particle equation. And actually would like to address this. But first of all, let's take away the Bethe-Salpeter equation and just look at the independent particle approximation. Also, it's not correct because it doesn't account for exciton binding, but we can learn quite a bit from this picture. What you see here are the Conchem orbitals for the LUMO, LUMO plus 1, LUMO plus 2, LUMO plus 3, LUMO plus 7, and so on. And I would like to point out what the character of this excitation is. So first of all, remember that we are exciting the nitrogen 1s levels. Nitrogen are this bridge here, and that's quite clear that since we have very high electron density here, that we have strong overlap between the core states and the density at this point. And that means that this A transition, the strongest one here, is formed by the 1s state going to the LUMO. This is this very sharp peak here. Then if you go up the molecular orbitals, the next one doesn't have any density here. Also L plus 2 doesn't have any density here. But L plus 3 has a small intensity here. So again, we would expect overlap between the core state and this one. And that's why we have a peak here. This is the peak B going to LUMO plus 3. But it's much lower in density because we don't have much density at this bridge here. But then if you go up, the molecular orbitals, L plus 7 is again a state where we have very strong density contributions from this nitrogen bridge. And this is the reason why we have a strong peak here, which is formed by C. So these Conchem orbitals, the character of these orbitals tell us already about the character of the excitations that we can expect. Now, what is worrisome so is that these peaks here, the spectrum, doesn't care at all about the neighborhood of the molecule. So it's exactly the same in the molecule or in the packet structures. How come? Well, it's not so surprising because these molecules are held together by van der Waals forces. So there is hardly any overlap in densities or wave functions. So it's clear that these molecules don't talk to each other very much in the ground state. Okay. However, and now this brings me to the Bethe-Salpeter equation, they're supposed to talk to each other in the excited state. And you can clearly see that if you go from the single molecule to the packed structure, these peaks shift. And this is an indication for the molecule talking to each other in the excited states. So now, in the excited state, we would see Bethe-Salpeter equation goes from the independent particle away, a picture away, and mixes the transitions, forming these strong excitonic peaks, A prime and so on. And you see here for the molecule, for instance, we have huge exciton binding energies, 6 electron volts. You go from this independent particle peak A here to A prime. So this is an extreme case of binding energy. And this is the answer to one of the questions where we had one, I think, correct solution. The core states of molecules have really, really high, extreme high binding energies. So peaks B and C, they shift, but they have a little bit smaller binding energies of roughly 4 electron volts in the molecule. And as you see here, by blue shifting the spectrum, for the packed SEM, the binding energy is going down. The reason is the expansion of the exciton wave function. So if a single molecule, electron and the hole, they sit on the same small molecule, they cannot avoid each other. That's why they are so strongly bound. But if they have a neighbor very close by in the excited state, the electron could somehow go away a little bit further from the hole, making the exciton wave function a little bit more delocalized. And this diminishes the binding energy by as much as 2 electron volts. So, well, Bethe-Salpeter equation is pretty cumbersome to compute. So if you think about ground state calculations, they scale with the third power of the number of atoms that we have in our system. GW, Bethe-Salpeter scale with the fourth power. So this is a huge computational effort to do, in particular if you have complex large systems to treat. So you may think about, is there an alternative that we can use to get the same answer? And yes, this alternative actually existed even before we were using Bethe-Salpeter equation for computing core states. And well, we go from a single cell to a supercell. So why that? Typically, as I said, since the scaling is so bad, we would like to have the smallest possible cell in order to treat our many-body system. But our way out, or our alternative, is to construct a bigger cell and to put an electron in the hole to the supercell. So what we do here, we know that we want to excite a certain edge. So we take away from a certain atom the core state that we would like to address. So this leaves basically a core hole, a hole in the core. But then we need to put this electron somewhere because our system has to be neutral. So we put it to the conduction bands, and then we perform a density functional theory calculation having this electron and the hole built in. And that way we somehow we burn this electron hole pair in a self-consistent DFT calculation into the system. And so we go away from DFT to constrained DFT, with constraint being this electron hole pair introduced here. So this comes with additional cost for the ground state because now we have a bigger cell, but DFT has a better scaling. But then if we go up into the spectroscopy, we have to compute the spectra only in the independent particle picture because the electron hole pair is already there. So we have it already burned into the system. So this is what is called the supercell core hole approach. It's pretty popular, I think, among theorists in core spectroscopy. But having the, let's say, probably more exact tool in hand, we now can probe how good is this approach by stringent comparison. So this is one example. It's the L2-3 edge in magnesium, a magnesium edge in magnesium oxide. So first of all, forget about the independent particle picture. This light green curve, it doesn't give you the right thing. So excitons are obviously very important here. But then you see the two solutions. One is the solution of the Bethe-Salpeter equation in yellow, and the other in green is the supercell core hole approach. So you see the peak structure is very similar, but there's distinct differences. So in particular in the oscillator strengths. So question, which one is better? Okay, we probe it against experiment. So what we see here is 3 different experiments for the same material and the same edge. And going from top to bottom, it has increasing resolution. So if we only had the first experiment with bad resolution and the supercell core hole approach, the green curve, you would argue this is perfect agreement. No? So having a bad experiment and a bad calculation, I mean, this is you can get perfect agreement, but actually we can do better. And if you now see how this peak structure, these strong excitations pop up here, if you make the experimental resolution better, all these 2 peaks, at the same time, you see that this Bethe-Salpeter equation gives you the much better picture. So in essence, the core hole approach gives you something which is, I think, qualitatively, I think, a good solution, good and quick solution. If you're interested in quantitative comparison, the Bethe-Salpeter equation is better. And you also see this in the next example. This is lithium fluoride, the lithium K edge, where you see that this very sharp onset exciton is very well captured by the Bethe-Salpeter equation, but the core hole approach underestimates the binding energy. And the reason for this is because in the Bethe-Salpeter equation, we treat the electron hole interaction explicitly, exactly, whereas in the supercell approach, we treat electron hole interaction on the same level as we treat the electron-electron interaction with this exchange correlation functional, which may be not strong enough to bind the electron and the hole. So let's get back to Bethe-Salpeter equation. I think I'm running short in time. We have calcium L2-3 edge in calcium oxide. We have a strong spin-orbit splitting of 3.7 electron volt. And you see here comparison with experiment is excellent in terms of the positions of the peak, but also the relative intensities. And since I think I'm running out of time, I don't want to bother you with details here. So this is the green and the blue curve are from the 1/2 L2 and the L3 edge. So the distance between these two is the spin orbit splitting. There you can see if you perform the calculation for the full system and then separately for L2 and L3 and taking the difference, then you see what the mixing between these two states is. What is very important, but I'm not going to point this out right now, is that in this case we have found extreme influence on the local field effects, which are crucial in Bose in this direct or in the exchange term of electron-hole interaction, but also through the screening of the dielectric function. So at the very end, I have one more example that I want to show, namely the fingerprinting. Here you see, for instance, the aluminium L2-3 edge in aluminium nitride in 3 different structural conformations. So we have rock salt, quartzite, and zinc blende. And there you see that these 3 materials, which come with different environments of these atoms, have their individual fingerprints. For instance, here we have a strongly bound exciton below the absorption onset, which is given by the gray line, whereas the other structures have the individual experiments. Now again, I can show you the electron hole wave functions and for the lowest excitation, and then you see that these 3 materials really have very different excitations in character. But this is something I think fingerprinting is known for. You have different structures, different environments of an atom, where you can get a signature of this environment from your core spectra. I'd like to show another example, which I think it's a very nice complementary, let's say, analysis coming from theory compared to experiment. So in this case, our experiment is an LNS experiment in the electron microscopy group of Christoph Koch. What you see here is beta-gallium oxide. This is a monoclinic structure. It has 10 atoms in the unit cell, and 5 of them are non-equivalent. So we have 2 different species of gallium, one of them octahedrally, the other tetrahedrally coordinated, and we have 3 different species of oxygen. And what we explore here is the oxygen K edge. Now, experiment, of course, the oxygen 1s level is basically the same, the energy. So from experimental point of view, it's very hard to distinguish between these different excitations. From the theory point of view, of course, we can probe the excitations of different atoms individually, so we can tell which of this oxygen contributes which piece to the total. To the total answer. So, as you see from the agreement, very good agreement between theory and the experiment, we are in a good position to explain or to interpret the experiment. And I have to say so here, the broader range of this experimental spectra, this broadening is simply due to missing resolution of the experiment. So we're getting a better microscope, but this is still done with what we have right now, or the university has. So let me go into this analysis a little bit further. The nice thing with electron microscopy is that you can choose different index planes that you can probe. So for instance, you can probe the 001 plane, or the 200 plane. So you cut your sample basically in different planes and then see what the response of your system is. So these are, again, the comparison of theory and experiment, pretty good. In both cases, so we have a peak structure of two significant peaks with some kind of a shoulder in between. So you couldn't tell a big difference from these two. So both look like potatoes, isn't it? So, but theory can do more. We can do it atom resolved. And I need to admit, so we didn't do any surface calculation, but we used a tool that we developed that allows us to rotate the dielectric tensor such that we can somehow mimic the experimental setup. And this is the answer. So surprisingly, for the 200 plane, we see that these two main peaks come from oxygen 2, one and oxygen 3, and this back here, this camelback comes from oxygen 2. Whereas for the 001, it's the opposite. So we have the two peaks here formed by oxygen 1 and oxygen 2, and the oxygen 3 is different. So we think that combining this knowledge from theory and experiment, where we can tell which of the features come from which of these from atoms, adds another tool to the idea of fingerprinting for systems which have low symmetry and where you have different environments of one of the same atomic species in one sample. So it's not separate in different crystals, but inside one crystal you have different environments of one atomic species, like here. So this brings me to basically the end, but I also would like to introduce to you our instrument. It's the most exciting one, of course. It's called exciting. So I can either read the paper we have written about or visit our web page. The exciting code is based on the full potential all electron method, LAPW, so implements the linear segmented plane wave method, which is considered to be the gold standard of solving density functional theory and the like. So very important, it's an all electron full potential code. That means we don't do any approximation to the core states. We don't use pseudopotentials. We solve the real potential there. And this allows us to treat all states on the same footing, going from the 1s state up to the conduction state. Everything is solved on the same basis, so to say. And that's why we can explore core states and also core spectra pretty reliably. So we have a focus on excitations, microscopy, spectroscopy, like photoemission, absorption, second harmonic, X-ray scattering, dichroism, electron loss, Raman spectra, optical maps, STM. As an Outlook, I also want to tell that we are working on an implementation of resonant inelastic X-ray scattering GRICs, where we have already some promising first results. And we have also implemented the Q dependence, which I have not shown yet, but this is also in place. And if you're interested to work with this code, I take the liberty to for an ad, because we're organizing a hands-on workshop on the code where you would get not in 1.5 hours crash course all the electronic structure theory, but in a few days, so from 31st of July to 5th of August, there would be tutorials and hands-on lectures on all the tools that we develop. And the last 3 days are dedicated to an international workshop with renowned speakers on the top-notch level of spectroscopy theory and experiment. So the official deadline is already passed, but if you're interested, send us an email and we probably can accommodate a few more people. So with this, I give you a snapshot or some recent snapshot of the group. I'd like to point out the main players here. Christian Vorwerk has implemented the fully relativistic beta beta for the core, also the Q dependence to some extent. Dima Nabok is our Green's function or GW expert. Andres is making the code as precise as possible, but he has also sped up beta beta such that we can run it for larger systems now. Katarina Koki has calculated the molecular crystals. She's and Ajana Manoharan is a PhD student working on cassiterite materials. And with this, I should also mention that all the data that we have published can be found in the NOMAD repository. So you can find all the input and output files It's a data repository for ab initio calculations. There's more than 50 million of calculations right now. You can find them here, and this is basically it, and I would like to thank you for your attention.
Thanks, Claudia, for this tour through theoretical spectroscopy. We have 10 minutes for questions.
Just a quick question regarding the calculation of wave function for electrons and hole pairs.
Mm-hmm.
Is it a joint density function, or is like the core is fixed and then it's calculated the electrons distribution?
No, I mean, typically, this is a six-dimensional object. By the way, you can look up there. We have some YouTube movies with virtual reality tools such that you can explore these objects, because otherwise it's hard to visualize. So because you have 6 coordinates. So if you want to plot this for a valence state, you have to fix one of these coordinates, either the electron and the hole, and then you can plot the other around. For the core states, it's easy because we know where the core is, because in this case, we have excited the aluminium 2p state, so we know that the hole is sitting at this aluminium atom, and then we can plot the electron distribution around. So for core excitations, we basically boil down the 6-dimensional object to a 3-dimensional one, and then it's easy to visualize.
So just want to confirm that the positive charge is fairly localized, just at the
Yes, just at the hole, because I mean this is the state you have taken out. For valence state, you can do the opposite. You can fix the electrons and see how delocalized the core is. But for core states, this is not needed. So in that sense, core spectroscopy is in a better position to get direct insight into the shape of the electron hole pair.
In the code, do you use a spherical harmonic expansion for
Yes. Well, in the code, LAPW somehow uses the best of two worlds. So around the atomic positions, we use atomic functions for a basis function. That means solutions of the radial Schrodinger equation times spherical harmonics. It's an expansion like this. And outside the spheres, which are non-overlapping, we use plane waves. And each of these plane waves, so it's called augmented plane wave method, each of these plane waves, when it enters a sphere, so to say, it's augmented by a linear combination of such functions, atomic-like functions. And in addition, we use so-called local orbitals, which make the basis even more flexible. So these are atomic-like functions that only live in the sphere. Particularly important for unoccupied states in order to improve the basis sets for spectroscopy. Say it again? Yeah. Okay, so we make these ansatz basically for the electron hole wave function. So knowing the conduction or the core states and the unoccupied states from the ground state, we combine them to products of these two, and then we use all possible products that we have for our k points as a basis for the two-body equation. Okay? So for the ground state, we use LAPW, so to say, as the basis. Here we use the conjunct states, the products of conjunct states of the basis, but they, of course, are built up by this LAPW basis again. And this ansatz enters the two-body wave function, and it collects, such an electron hole pair collects then contributions from all kinds of independent transitions. You sum up over all these contributions with the corresponding coefficients.
More questions? Yeah, there's one more.
Can I have a question? Do we usually calculate the light
The lifetimes? Not yet. Actually, in order to get the lifetimes, you need to compute the imaginary part of your self-energy, of your Green's function. So we have some results for the electronic lifetimes, not yet for the lifetimes of the electron-hole pairs. But it's something which is very very interesting and important, and we keep an eye on this. Yes. Yes.
Challenges. Where are the problems and what does it take for example, to do molecular rigs on transition methods when you're looking at nitrogen?
I mean, the implementation is basically there with all the ingredients we have already. The complexity comes from, it's a computational complexity, because it's not only one of these huge matrices, but then you combine these huge matrices, and this gives you a hard time in what you can somehow store in your memory and things like that. Yeah, but I think for simple system we have already some results. For complex system, it's really a computational challenge at the moment.
When you say complex and simple, what do you mean?
Simple means, I mean, 2 atoms per unit cell or something like this. So structurally simple materials.
But you don't need the crystal typically, right?
We
You could do it on molecules.
could do it on molecules, but for us, molecules are much harder to compute because we have a 3D periodic code. That means if you want to compute molecules, like I've shown, we need to put it in a very, very big box. The box must be big enough in order to prevent interaction between these neighboring sites. It's doable, but it's then even more costly than a periodic crystal.
No more questions, then first of all, let's thank Claudia, but then also Amy has an announcement to make. So let's first thank Claudia.